We talked about gradient of a scalar field in section 9.7. Now we want to talk about divergence of a vector field. In 9.7, we talked about the gradient. If you have a scalar field, you can apply gradient to get a vector field. Now here, if you have a vector field, we can apply divergence to get a scalar field. Or we can apply curl to get another vector field. So these concepts have a lot of applications. I'm going to show you a lot of applications of these in physics and engineering. And the divergence is basically defined by this expression. If you have a field vector v as a function of x, y, z, means that to each point in space, you assign a vector that has three components, v1, v2, v3. And if it is differentiable, the divergence of v is defined by a scalar, that is the partial derivative of v1 with respect to x plus partial derivative of v2 with respect to y plus partial derivative of v3 with respect to z. So this is called divergence of v and can be written as, there's a typo here, it should be v, divergence of v equals to del dot v. Remember the del operator we defined last session? It was an operator like this. It's a vector that has three derivatives: partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Now you can make the dot product of this operator with the vector v. So it becomes partial of v1 with respect to x, partial v2 with respect to y, plus partial v3 with respect to z. So this is like that, like del dot v or nabla dot v. So this is the definition of divergence that you can write as del dot v. This is an example. If v is this vector field, which you see the x, y, z components are function of x, y, z, and we can write it like that, the divergence is simply the derivative of this part with respect to x, which is 3z, plus derivative of this with respect to y, which is 2x, and plus derivative of this part with respect to z, which is negative 2yz. So you add all these three, you get a scalar that's called divergence of v. And this is an example gravitational field of a point mass at the origin. Remember from the Newton's law of gravitation, if you have a point mass with capital M, mass capital M at the origin, at any point in space, the gravitational field can be written as this: G, which is gravitational constant, times the mass, divided by r squared, times the unit vector in the direction of r, but with negative means that it is directed toward the origin. So we can write it like that. And because we want to take derivatives, we should write it in terms of x, y, z. So you see this r is x I hat plus y j hat plus z k hat, and r cubed is x squared plus y squared plus z squared to the power 3 half. And again, because we want to do derivative, it's better to write it as the product, not the fraction. We can write this as this denominator. You can come up with the negative power times that. All right, so if you want to take the divergence of G, that will be the with constant times partial with respect to x of the x component, which is this x times this expression, and the same with the constant in front of it, partial with respect to y of the y component, which is y times this expression, and the same for z, partial with respect to z of z times this expression. So if we want to calculate the divergence of this expression, it involves all of these. So let's do that. Divergence of G becomes this constant term. Now we want derivative of this one with respect to x. And this is a product. So we need to use product rule. Becomes and derivative of x with respect to x times this part plus x times derivative of the other part. All right, so that's derivative of s with respect to x, which is 1 times that, plus x times derivative of this part, which is -3/2 times this expression to the power 1 less than -3/2, which is -5/2, times the derivative of what is in here, this expression from chain rule, which is 2x. All right, and then for this one is the same, derivative of y with respect to y times that, plus y times derivative of the other, which is very similar. Again, for z is also similar to that. So you see that these there are 3 terms like this and 3 terms like that. So these 3 terms you can add up, and of course -gm is factored, and you have 3 of these terms, and then these ones. For each one of these, you see it's a 2 that cancels, and you have a -3, and then you have x squared. And this here you have y squared. Here you have z squared. So if you factor the -3 and this expression, you have x squared plus y squared plus z squared. So -3 x squared plus y squared plus z squared times the square plus y squared plus z squared to the power -5/2. But this is power 1 minus 2.5 becomes -1.5, becomes the same as that. And 3 of that minus 3 of that gives you 0. So everything cancels out here. So the divergence of G, the gravitational field of a point mass in space, is 0 everywhere other than origin, of course. This is not defined in the origin, so we can only talk about the divergence at any other point other than origin. Any questions so far? All right, so this is for point mass. Now I'm going to take it one level. What about the gravitational field of a uniform sphere of mass m and radius r centered at the origin? What does it mean, uniform sphere? It means that the mass that it has, m, is uniformly spread over its volume inside radius r. It's like the Earth, for example. You have the Earth, it has a radius. If the density of the mass inside Earth is uniform, which is not, but it's close, then that will be this model. So if r is less than the radius, means that you are inside the sphere, the gravitational field is a constant times r, means that it increases by the distance from the center linearly. But if you're outside, it will be the same as before, which is like a point mass. Outside the spherical mass acts like a point mass. This is called shell theorem in electromagnetism. It is also the same in gravity. So for outside, when r is greater than r, is the same as before. So we know that divergence of G is 0. We just took the divergence of this and we showed that it is 0. But what about inside? Inside, if r is less than r, divergence becomes divergence of this expression. But this expression, you see, it has a constant here. The constant comes out of the divergence, becomes like that, and becomes divergence of r. What is divergence of r? It is the del operator dot the r vector. And that means the partial of x with respect to x plus partial of y with respect to y plus partial z with respect to z. And each one of those is 1. So -gm over r cubed, 1 plus 1 plus 1. So it becomes -3gm over r cubed, right? Does it make sense? Any questions so far? All right, now let's look at this, see what this is. You can bring this 3 to the denominator and multiply by 4 pi. If you multiply both numerator and denominator by 4 pi and bring this 3 to the denominator of denominator, you have 4 pi gm divided by 4/3 pi r cubed. And this 4 pi r cubed is what? is the volume of the sphere. This is mass over the volume. You can replace it by the mass density. So it becomes negative 4 pi g times rho. So for r less than r means that inside the sphere, the divergence of g is negative 4 pi g times rho. But because outside the divergence was 0, and also the density of mass is also 0, so you can say everywhere the divergence of g is equal to negative 4 pi g times rho. The inside was that because there was rho and it's constant, and outside rho is 0, therefore this expression becomes 0, therefore divergence of g is 0. So this expression works everywhere, at least for this example. But it turns out this expression is always true for any mass distribution. And this is called the differential form of the Gauss law for gravitation. You remember in electricity magnetism, we have Gauss law for electric field. Gauss law for electric field is divergence of E equal to rho over epsilon naught. Of course, you haven't seen this form of Gauss law maybe, but this is called differential form of Gauss law. You have seen the integral form of Gauss law. And there is a relationship between this differential form and integral form. They are equivalent of each other. Why they are equivalent, we don't know until next chapter. In next chapter, we're going to talk about the surface integrals and Gauss theorem and all of that, that we can show that this differential form is equivalent of the integral form that you have seen in electricity magnetism. It says divergence of E equal to the density of charge at any point divided by epsilon naught. Okay, so the same equation applies for gravity, almost, you see, because this rho is always positive, but gravity is attractive, so divergence becomes negative here. But here, rho can be positive or negative. If rho is positive, divergence is positive. If rho is negative, divergence is negative. And because Coulomb's law and Newton's law of gravity both have the same mathematical form, it turns out to be the same mathematical form here as well. Any questions so far? Okay. Now, double derivative and the Laplacian. We talked about the gradient of a scalar field. As you remember, gradient of f is del f over del x, I, del f over del y, j, del f over del z, k. Because the gradient of f is a vector field, you can apply divergence to it. So divergence of gradient of f is this. This is divergence, which is del dot gradient of f. What this means is that you need to take derivative with respect to x of this expression, derivative with respect to y of this, derivative with respect to z of this, and add them up. So it becomes like that. So it becomes second derivative of f with respect to x, plus second derivative of f with respect to y, plus second derivative of f with respect to z. We call this expression the Laplacian of f, and we denote it by del squared of f. It's just like del dot del, we call it del squared of f. So del squared of f is given by that. This is a Laplacian operator that operates on a scalar field and gives you another scalar field. All right, so this is called Laplacian, and this is called Laplacian operator. Any questions? All right. So the next example I'm presenting here is potential theory. In electromagnetic theory, the electric potential function phi, a function of xyz, is the line integral of the electric field from a reference point to a point r, xyz. We will study that in the next chapter. We haven't talked about line integral. We're going to do that next time. It turns out that the electric field becomes the negative gradient of the potential function. So the potential function is a scalar function. If you take gradient of that, it becomes a vector function, which is the electric field. And we saw that divergence of E at any point in space is related to charge density. So divergence of E is rho over epsilon naught. Divergence of E calculated at any point xyz is equal to the charge density at that point divided by epsilon naught. This is, of course, in free space when there's charge density, but there's no dielectric material. But divergence of E can be written as divergence of gradient of phi with a negative sign, which is negative del squared of phi, and that becomes equal to that. So you can write this. Usually we derive xyz. This is, we know implicitly that these functions are functions of xyz. They are scalar fields. So we drop the xyz. We write it this way. We write del squared of phi, or Laplacian of phi, equal to negative rho over epsilon naught. This is called Poisson equation in electrostatics. If you are in free space with no charges, then rho is equal to 0. This reduces to Laplacian of phi equal to 0, which is called Laplace equation. So this is again another application of Laplacian, and this del operator and divergence and gradient. Any question? All right. Another example, which I took from the book directly, but I made a little bit of changes, is flow of a compressible fluid. The physical meaning of divergence will be clear in this example. We consider the motion of a fluid in a region R having no sources or sinks in R, that is no point at which the fluid is produced or disappears. Fluid is usually a collective name for liquids, gases, and vapors. Also anything that takes the form of its container. It's called fluid. So gas is an example, vapor is another example, liquid is another example. Some fluids that are liquid, such as water or oil, have very small compressibility, which can be neglected in many problems. So if they are liquids, usually they have low compressibility, but gases have high compressibility. You can compress a gas. You cannot compress water or oil. You can, but very, very minimally. So the compressibility can be ignored. But gases can be compressed or expanded. Here we assume our fluid to be compressible or not in a general case. So we want to consider the flow through a rectangular box of the small edges, delta x, delta y, delta z. We want to see if there's a flow of liquid or fluid in general. What is the net mass going out of this box? So let's start with the fluid having the velocity field vector like that. This is general. Velocity field vector has an x component, y component, z component. X component is v1, y component is v2, z component is v3. You can write it this way as well. But we have u equal to rho times v. So v is the velocity vector field. U is the rate of mass flow, we call it, because rho is the mass density. If you multiply it by v, you get rate of mass flow. That also has three components, u1, u2, u3. Of course, u1 will be rho times v1, u2 will be rho times v2, and so forth. So you can write u as this. So it is convenient to introduce u because this factor rho appears everywhere. It makes it simple to just introduce u so that you don't have a factor tagging along all the time. All right, so we assume that this function u or v are continuously differentiable vector functions of x, y, z, and t. Means that they have first partial derivatives that are continuous. And then, okay, these are our set. The most important part is this part that I'm going to take to the next slide. So we have rate of mass flow vector field and this box. So I want to see how much mass is going through the sides of or faces of this cube. Of course, this cube is very small, but we show it larger to make it visible, but it's very small. So let's see how much mass goes through these faces. There are 6 faces here. There's a left and right, which is left is this one. The right one is the one that you don't see in the back here. So we have left and right, we have back and front, we have top and bottom. So I call them left and right, back and front, and top and bottom. So now consider the flow through the left of the 3 faces of B. Okay, that is this one. That is at y equal to y, and you see all the y coordinates are the same on this face, and the area is delta x delta z. Now, if you want to see how much mass goes into that, you see V1 and V3 means the first component, x component of V, and z component of V are parallel to this surface, so they don't contribute into flow of the material inside this one. But the only one that contributes to that is the second component, which is y component, which is perpendicular to that face. And rho times V evaluated at y times the area times delta t becomes the total mass that goes through this space at the time delta t. Because this, when you do rho times V, it gives you mass per unit area per unit time. If you multiply it by unit area and unit time, you get the total mass that passes through this face. All right? And you can write that instead of rho V, rho V2 becomes U2. So it becomes U2 evaluated at Y times delta X times delta Z times delta T. That's the total mass that goes through this face. Any question? All right. Now, we want to see the total mass that goes out of this other face, the right face. The mass of fluid leaving the box B through the opposite face during the same time interval is this. Rho V2, again, V1 and V3 don't contribute to that because they're perpendicular to that face. But V2 evaluated at y plus delta y, because the y component of velocity may be different here than on the other face. So maybe, for example, slower here, faster there. So here is the amount of the velocity at that face times rho times the area times delta t. Or again, rho times V2 can be written as U2. So U2 evaluated at y plus delta y means on that face times delta x delta z delta t. So the total mass that goes out of these two together is the mass going out of the right face minus the mass going into the left face is this. And you can divide this by delta y and multiply by delta y. We want to multiply by delta y to make this delta x, delta y, delta z. So if you do that, you get this expression, and this one becomes delta v, means the whole volume of this box, and this one becomes delta u2 over delta y. So it becomes delta u2 over delta y, delta v, delta t. So this is the net amount of mass that goes out of the box through the left and right face. So I take this to the other slide. So you see, that says what I just said. The net mass of fluid going out of the box through the left and right faces is this. And this is just showing the derivation again. So similarly, the net mass of fluid going out of the box through back and front faces is this. You see, in back and front faces are perpendicular to the x component, x direction, right? So the only component of u that contributes into that is u1, the x component. And the x component of u evaluated at x plus delta x means on this side, which is front face, minus u evaluated as x means back face, times delta y delta z, the area of those faces. So delta y and delta z is the area of these two faces, times delta t. And then again, you multiply by delta x, divide by delta x, so you get the volume here, and you get this. So you get delta u1 over delta x, delta v, delta t. So that is the net mass of fluid going out of the box through back and front faces. And the same for top and bottom face, net mass of fluid going out of the box through top and bottom faces is this. You see, again, only the third component, the z component that is perpendicular to top and bottom, contribute to that. And u3 evaluated as z plus delta z minus u3 evaluated as z times delta x delta y, the area, times delta t. All right? And then if you divide by delta z, multiply by delta z, you get this expression, which you can write as delta u3 over delta z times delta v times delta t. Okay? Each one of these is for one pair of parallel faces. So if you want the total or the net mass of fluid going out of the box through all faces is sum of all these three. So it becomes delta u1 over delta x, delta v, delta t, delta u2 over delta y, delta v, delta t, delta u3 over delta z, delta v, delta t. Of course, you can factor delta v, delta t, and you get this. All right? So this is the net mass going out of this box. So let's take this to the next slide. Any questions so far? So far, we calculated the net mass going out of this box. So I'm going to take this to the next slide, and I call that negative delta m. Means that how much this mass that goes out of this box changes the mass inside the box, and of course changes in negative direction. Now, if you divide by delta v, delta t, we get this. Get this expression equal to negative delta m over delta v, delta t. I can put this delta v over m. You see, this is the mass of the fluid inside the box divided by the volume of the fluid inside the box, becomes the density of the fluid there. So it becomes negative delta rho over delta t. Okay? Now, let's look at that when delta t goes to 0 and also delta x goes to 0, delta y goes to 0, delta z goes to 0. At the limit, when all of these go to 0, you can write these as partial derivatives. Of course, u1, u2, u3 are all functions of x, y, z, and t, and rho is also functions of x, y, z, and t. Here we talk about partial derivatives of these. So this becomes partial of u1 with respect to x, partial of u2 with respect to y, partial of u3 with respect to z, and partial of rho with respect to t. So the expression becomes like that. But is this familiar? Do you remember what this expression is?
Isn't that just the divergence?
That's divergence of u, yes. So divergence of u, which is divergence of rho times v, remember u was rho times v, becomes equal to negative rate of change of rho at time t. Of course, this happens at every point in space, x, y, z. You usually don't write x, y, z. If you write, it should be x, y, z, t, x, y, z, t, x, y, z, t. They are all functions of x, y, z, and the time. So at any point in space and at any point in time, this equation holds. So we write it like that. Usually we move this to the other side, makes it positive, and we write it like that. This is our equation of continuity or condition for conservation of mass for compressible fluid flow. So when you have a compressible fluid flow and we don't have a sink or source inside the region, this equation holds. So you see that this divergence means that how much of this field goes through the surface, of course, when the box shrinks to zero at that point. So this is the meaning of divergence. And of course, we don't define divergence like that because we haven't talked about, in general, haven't talked about how to calculate the divergence in that sense, means the flow of the flux of the field through the surface. We're going to do that in the next chapter where we talk about the surface integrals. So in some physics books, they introduce divergence with that surface integral, and then they show that the divergence has a form like this in mathematical form. So these are two different ways of looking at the divergence. So this is the condition for conservation of mass or continuity equation for compressible fluid flow. And there are some special cases. For example, if the flow is steady, means that it is time independent. If that is the case, then this time derivative becomes zero, then this equation becomes like that. So this is the same continuity equation, but for the steady situation, when things don't depend on time. And then when rho also is independent of position, means at any point, the density is the same like in water. The density doesn't change from one point to the other because the water is incompressible. And in that case, if rho is constant, this constant comes out of the divergence and can be canceled. Then we get divergence of V equal to zero. That holds for incompressible fluid, or they call it condition for incompressibility. Any questions?
You divided the row out?
Yes.
Okay.
If rho is constant, comes out of the derivatives, and then it's a factor of this equal to zero, but rho is not zero, so it means that the divergence should be zero. All right? So this is condition for incompressibility. This is the general form of the continuity equation. This is when you have a steady state, means nothing changes with time. This is when rho is constant. Of course, if rho is constant in here, it means that it doesn't change with time and doesn't change with the space. Again, you get this equation. Any questions? All right. So that was all section 9.8 about divergence. Now in 9.9, we talk about curl of a vector field. If you have a vector field like this, suppose it is differentiable, all of that, the curl is defined like that. Curl of V is L cross B, which is, the determinant with ijk here, the components of del on the second row, and components of V on the third row. And then when you want to take the determinant, again, take I and then eliminate row and column of that, and you get this determinant. This means that this multiplied by that minus this multiplied by that. So it becomes del V3 over del Y minus del V2 over del Z. And then negative J times the determinant of this, del V3 over del X minus del V1 over del Z, and so forth. So you see, they don't usually put this negative, but you see that these two terms are switched the first they write del v1 over del z minus del, because there was a negative sign here, and then they absorb the negative sign, they switch these two, and the same here. So you know how to calculate the cross product. This is cross product of del operator with the vector field. All right, is there any questions? So del cross is actually the curl. Sometimes they write curl, sometimes they write del cross. Again, with the same del operator that you know. An example of this from the book is simply if you have a vector function like this, you want to calculate the kernel of that, you do the determinant ijk, partial derivatives, and the components, yz, 3zx, and z in here. So if you eliminate the row and column of I, becomes del z over del y, which is 0, minus partial of this with respect to z, which is 3x. So that's why you have negative 3x times I. And then negative j times partial of z with respect to x minus partial of yz with respect to z. You get y, get negative and negative, get positive. And then k times partial of this expression with respect to x, which is 3z, minus partial of this expression with respect to y, which is z. So 3z minus z times k. So it becomes like this. This is a simple example of the curl of a vector function. Any question? All right. This is an example from the book. We remember the rotation of rigid body that we talked about. We said that if something is rotating with angular velocity vector w, which has a magnitude of omega, if the axis of rotation passes through the origin, we can write the velocity vector field of the points on the object that's rotating as w cross r. That's what we did in the section 9.3. If the z-axis is taken as the axis of rotation, we can write w as the magnitude of w in the z direction. So the magnitude of w is usually written as omega. That's the angular speed, omega, in the direction of k hat. And then v, which is omega cross r. R is x, y, z. If we do cross product, you see that we did that before. It becomes negative omega y and omega x and 0. Okay? Or you can write it as this. And now we want to see what is the curl of this velocity vector field. And the curl of v becomes ijk, the partial derivatives, and then the components of v, which is x component is negative omega y component is omega x, and z component is 0. Okay, and then what is this? Now, if you take the I, eliminate this, you get 0 minus a partial of this expression with respect to z, which is 0. So I times 0. J becomes 0 minus 0. That is also 0. K times partial of this with respect to x, which is omega, minus partial of this with respect to y, which is negative omega. So omega minus negative omega becomes 2 omega. So it becomes 0, 0, 2 omega. So that's the curl of this velocity vector, which is 2 omega times k hat. This is the unit vector notation. All right, so that is actually twice the w vector that we have. So that proves the following theorem. Whenever you have a rotating body, the curl of the velocity field of a rotating rigid body has the direction of the axis of rotation, and its magnitude is equal to twice the angular speed of the rotation. That is true in general, that we showed in a special case here. That's a theorem. All right. Any questions so far? So the question, what is this here? Every object that is rotating, every point of the object moves at a certain direction that defines a velocity vector field around the axis of rotation, right, in space.
Oh.
Here, what we're showing is that the curl of that velocity vector field is equal to twice the original angular velocity vector. This only shows what the curl is. And from the right-hand rule, if you put your 4 fingers in the direction of the velocity of the objects, the velocity of each point around the axis, your thumb shows the direction of the angular velocity vector. All right? That is why they say curl shows the rotation of the vector field. So if vector field is rotational, it has a curl. If it doesn't have a curl, it means that it is not rotational. It's not like something that's rotating. Okay?
Okay.
Whatever is rotating, it has a curl. That's why when a vector field has curl, they say it is rotational field. That doesn't mean that necessarily is rotating, but it looks like rotating. I will show more examples later.
Okay.
Any other questions? So that doesn't mean that there's anything physically is in that direction of angular velocity. It just, the curl of the velocity vector field is in the direction of the original angular velocity vector that was there. It just shows that the curl shows the rotation. And therefore, whenever there's a curl of something that's not zero, they say it is rotational vector field. With more examples, it will be more clear. I'll show you. So another theorem that we have in this book is that the gradient fields are irrotational. What does it mean? It means that if a continuously differentiable vector function is the gradient of a scalar function f, then its curl is zero vector, zero everywhere. So that's, again, you see the curl of something is zero, it means that it is irrotational. It means it doesn't look like a rotating thing. Furthermore, the divergence of a curl of a twice continuously differentiable vector function v is zero. Divergence of the curl is zero. These are mathematical results that comes from the definition of these divergence, curl, and gradient. And it is easy to prove if you just write down what it means, the gradient of f, you know the mathematical form of that, and then take the curl of that, you see that you get zero because all the partial derivatives cancel each other. And also here, if you take the divergence of curl, you get terms that cancel each other. It's very, very simple, but these are things to consider, very interesting. For example, if gradient of a potential function in electrostatics, gradient of a potential function is electric field, the curl of electric field in electrostatics is zero. Of course, curl of electric field in electrodynamics is not generally zero because of Faraday's law. All right, so let's go to the next example. Laminar flow of a viscous fluid, such as water, inside a tube has a maximum speed V0 at the center of the tube and stationary on the inner wall of the tube. The velocity field of the fluid flow inside a tube of radius r that is coaxial with the x-axis, I think this should be x in this case, x-axis can be modeled by this. You see this, the velocity field vector has an x component and it doesn't have y and z components. This is the cross section of the tube that has water moving in it. The middle of the tube, the speed of the fluid is larger. And as you go to the inner wall of the tube, the velocity of the particles becomes smaller and smaller. So you can model it by an equation like this. V naught over R squared times R squared minus Y squared minus Z squared. That's the X component. The Y and Z component are zero, means that we have only velocity vectors only in X direction everywhere. But if you are on the X-axis, means at the center, Y is equal to 0, Z is equal to 0, you get all 0, and R squared cancel, you get V naught. As you go the inner wall, Y squared plus Z squared will radially increase until it becomes the same as R squared. If R squared plus Z squared is equal to R squared, this also becomes 0, means that this fluid is stationary at the boundary, which is usually the case for viscous fluid. So this becomes a velocity vector field in this case as a function of x, y, z. Of course, it's not a function of x because it's the same everywhere along the x-axis, but it changes with y and z. So this is just inside the tube. Of course, outside there's no fluid, so the velocity is 0. You want to find the divergence and curl of the velocity field vector inside the tube. So let's start with the curl of V, means curl of this vector field. As usual, we can put the constant outside, and then we have ijk. The next row is the components of the del operator, the partial derivative. The next row is the components of the velocity vector field. So it becomes like that. And then this becomes I times 0 minus 0. So that's 0 times I. And then J times 0 minus negative 2Z, right? So we get negative J times negative derivative of negative 2Z. So there are 3 negative signs, gives you a negative 2Z, and then K times 0 minus negative 2Y. So it becomes positive 2YK. And you can write this as, if you factor the 2, get 2V naught over R squared, 0, negative Z, and Y, right? So the curl of V has this functional form. And the divergence, can you see the divergence is 0 directly? The divergence is the derivative of the first component with respect to X, which is 0 because it doesn't depend on X. The derivative of the second with respect to Y, derivative of the third one with respect to Z, and add them all up. They're all 0. So the divergence of V is 0. You can see it directly. So the curl is that and divergence is that. Let's look at what it means actually. If you zoom on this, you see that in here, let's say at this point, particles that are closer to the center are going faster, and particles that are farther from the center are going slower. From the point of view of this particle, it feels like the particles around it are rotating around it. You see, like if you are on a middle lane of a highway, and to the left of you, the cars are going faster, and in the right lane of you, the cars are going slower. In the frame of reference of your car, you see that on your right, they go forward, on the left, they go backward. So it looks like they're rotating around you in the, if you look from the above, in clockwise direction. So that's what we see here. These particles are moving faster, these particles are moving slower than this. Therefore, it looks like they're rotating around, even though they're not rotating, they're all moving forward. But from the frame of reference of this particle, feels like they are rotating. And of course, the curl at that point, you see, at this point, let's say X is this direction, Y is up, and Z is perpendicular to the page. And you see in here, Z is 0. Let's say X also 0, X doesn't matter. Z is 0 and Y is negative something, negative y naught, right? So if you look at this, z is 0 and y is negative y naught, you get a z component that is negative. The curve at that point it has a z component that's negative. It means that if z is out of the page, the curl is into the page. You can get that by using right-hand rule. If you put your right hand 4 fingers in the direction of this rotation that looks like rotation, your thumb shows into the page, means that the curl of this vector field is into the page at that point. Can you guys do that? Do you see that? I want you to put your 4 fingers in the direction of this apparent rotation, and then you see that your thumb of your right hand shows into the page at that point. And of course, if you go around the axis of this tube, you can do the same. If you rotate around, it's always tangential to this circle. So at this point, the field is into the page, and at any point is tangent to this circle. The curl of V is a rotating curve, rotating vector field. This one is actually looks like rotating, but the curl of it is actually rotating, which is tangent to this circle, which is coaxial to the axis of the tube. Does it make sense? Any questions? Do you understand what I'm saying?
Yep.
All right. So, and interestingly enough, I have another example that is exactly starting from that kind of field. And that, if you remember from electricity and magnetism, from magnetic field, this curl, which looks like this, is the magnetic field of a wire that has a uniform current going through it. Here, the magnetic field of a long, solid cylindrical wire of radius r, coaxial with the x-axis, carrying a total current I, which is spread uniformly over its cross-section as a constant current density, vector is the current density J, has a magnitude of J in the direction of x direction. J, the current density, is the current, total current divided by the cross-sectional area, pi r squared, of the wire. This is the illustration of the magnetic field. This is the section of the wire of radius r, current I passing through it, and the current I, total current I, is spread uniformly over its cross-section. From Ampere's law, you can calculate the magnetic field at any point at the radial distance of little r, inside and outside. Inside, where y squared plus z squared is less than r, or little r is less than capital R, you're inside the cylinder, the magnetic field is given by this expression. Outside the cylinder, when y squared plus z squared is greater than r, it's given by this expression. You see, they are both in azimuthal direction, means that this, at every point, the magnetic field is tangent to the circle. Plane of the circle is perpendicular to the wire, and it's centered at the axis of the wire. And the magnetic field is tangent to that everywhere. So it's circular magnetic field around the axis. But the magnitude of it is given by these values at different x, y, z position in space. Of course, nothing is depending on x because it's symmetrical along the x-axis, but it depends on y and z. You also have in physics books that is magnetic field is 0 at the center. This is the magnetic field magnitude as a function of the radius r, the distance r from the axis. And this capital R is the radius of the wire. And inside the wire, at the center of the wire, the magnetic field is 0. As you go away from the center of the wire, central axis, the magnetic field magnitude increases linearly. until we get to the surface of the wire at this point. And then after that, it reduces by 1 over r, or drops by 1 over r, so mu naught I over 2 pi r. And at the surface, they match, both functions match. So this is the illustration, and I want you to look at this function. See here, is a constant times 0, negative zy, and here is another constant, 0, negative zy. So inside, the magnetic field here is exactly the curl of this velocity vector field, which is very interesting. All right. Now, this magnetic field by itself has a curl. We want to calculate the curl inside and outside. All right. So for the inside, we have this constant, and then you have del cross D. This is the cross product by ijk, determinant, and the components of del operator and components of B. Of course, the constants all come out. And then what is this? This I times 1 minus negative 1, right? So this times 2I. And in J direction, you get partial of y with respect to x, which is 0. Partial of 0 with respect to z, which is 0. And in the k direction, also 0. So you get only this. You can cancel the 2 here, get mu naught I over pi r squared times I hat. But look at this. What is this I over pi r squared? You see, this is I, total current divided by the cross-sectional area, pi r squared, is this magnitude of the current density. And if you multiply that by I hat, will be the current density vector. We call it J vector. So the curl of B becomes equal to mu naught times the current density vector. But that is for inside. What do we get outside? That's for inside of the cylinder. Outside, we have this. We have the constant, mu naught I over 2 pi, times the curl of the rest of it. And of course, the next row will be partial derivative. The first component is 0 times that. The second component is negative z times that, right, here. And the third component is y times that. So we want to calculate this curl. See what we get. For I, we get mu naught I over 2 pi times I times the partial of this with respect to y, partial of this with respect to z. Partial with respect to y is, this is a product. We can say 1 times that. So let's say that's this. Partial of y with respect to y times this other expression. It's a product rule. Plus y times negative 1 times this expression to the power negative 2 times 2y, the derivative of what is inside with respect to y, which is 2y. So it becomes negative 2y squared, y squared plus z squared to the power negative 2. And minus the derivative of this one with respect to z. With this negative, minus becomes positive. Again, derivative of z with respect to z times this expression gives you another one of these expressions, plus the derivative of plus z times derivative of this one with respect to z. So get negative 1 times y squared plus z squared to the power negative 2 times 2z. So in total becomes negative 2z squared with that z times y squared plus z squared to the power of negative 2. Right? So you have 2 of these, and then these 2, you can factor the negative 2. Y squared plus z squared times this y squared plus z squared to the negative 2 gives you y squared plus z squared to the negative 1. So that all 4 terms become 2 terms that are similar, and 2 minus 2 gives you total 0. you see all of this expression reduces to 0. So that because that was a vector, that's a 0 vector. So you have inside the cylinder, inside the wire, the curl of B equals to mu naught times current density J. Outside the cylinder, the curl of B becomes 0. But you can look at it as it is 0 outside because there's no current density. So you can say everywhere, curl of B is equal to mu naught times J, the current density, right? Because inside the current density exists and curl becomes that, and outside the current density is 0, therefore the curl of B becomes 0. All right, this is the differential form of the Ampere's law. Again, I was mentioning that we have an integral form of Ampere's law in magnetostatics, but then in the next chapter, we're going to talk about some line integrals, what the curl really means, and there's a Stokes theorem that lets you transform a surface integral over a bounded surface into line integral over the boundary of that surface. And if you have that tool, then you can show that this equation is equivalent of the Ampere's law in integral form. That is the interesting thing. So the Ampere's law, also the same as Gauss' law, has two forms. One is integral form, and one is differential form. Differential form is here. All right, thank you for watching and have a good day.